And we'll just wait a few more minutes for people to peter in, I think, if that's the correct word, and I don't think it is. And at this point, before we've officially started, if either of you want to, introduce yourselves or, have a quick chat, that's totally fine by me. I'm clearly not shy. All right, welcome aboard. I think we might just, since we only have a few people, I think we might wait just a few more minutes if that's okay with everybody. Well, actually, I think I'm going to address everybody who's participating directly at this point. Hamid, Chung, or Anil, if anybody wants to share why they're here or what they hope to learn, that'd be great.
Sure. I am a cardiothoracic radiologist with some interest in creating some phantoms, and that's why I'm here.
You said some phantoms?
Yes.
Okay. Could you define phantom here, please?
Oh, so my goal is to create some coronary artery phantoms.
Reservations made on southwest.com may be changed or canceled on our website.
Sorry, Kenneth, would you mind muting yourself, please?
For your new flight may be available on southwest.com. To better serve you, please enter your date of birth.
All right, we get one of those every time. Sorry, please continue.
That's okay. Oh, so yeah, so my goal is to create some coronary artery phantoms. The problem currently is that we're comparing CT angiographies with interventional radiology, which is not definitely the gold standard accurate comparison. So I'm trying to create some phantoms so that we can improve our CT imaging.
Okay. What materials would you hope to use for this?
Well, I'm trying to get some ideas here. I used some more kind of like plastic material, but the problem was that I created all the phantoms, but the problem was that it was good for 2 or 3 weeks. And after that, it started to degrade and I started to get some air bubbles within the phantom and couldn't use them.
Okay, so it's is it like the properties of just like strength or resilience that matters most to you?
Well, the resilience is important, but the thing is that what I'm looking is something like, imagine that you have a tube and within the tube you have some material which I want to have a specific attenuation on CT.
Okay.
Which could be close to kind of like different a range of calcium, different concentrations of calcium within the tube, and anything within the tube other than the calcium is going to be just some contrast iodinated material.
Okay. So that's very interesting. I hope that you can at least get some inspiration from this talk. I'm mostly talking about copper in this, just because that's what I have the most experience in. But it's pretty much possible to print in whatever material you want with this method. It's not always possible to get a pure material with this method because you're mixing plastic with metal or the other material. But I'll talk about how you can get pure material, the steps for that.
Okay.
So thank you. I appreciate that. And with that, I think I might start our talk officially. So I definitely appreciate that. Because we don't have many people here, if anybody wants to interject or make a comment or a question, that's absolutely fine. This is about you, not just me talking about what I've done. And so thank you with that. I'm talking about FDM bound material printing. I'm Aaron. I'm from Lawrence Tech for a long time, Lawrence Tech in Southfield. I have a biology background, so I started studying lipid droplets, the organelles that store fat in your cells. And I have a biochemistry degree from Michigan State. I've also studied nematodes. I studied their chemotaxis behavior using computer vision when I was at Hebrew University. And then my master's degree is in biomedical engineering, also from Lawrence Tech. I studied abroad in Beijing, China for a little while. And now, as we can see, I am an adjunct and mentoring my own interns. So from high school intern to teaching my own, that's my legacy here. And a lot of what I've done in the past, I've given a couple of talks on this, is actually microphotography. So 3D scanning, especially for very small things. And so, I like to build things and, make technology out of stuff I find in the trash. And so we got some equipment that was suitable for this metal 3D printing method. And I said, let's try it. And this is what I've been doing for the past 8 months. So here I am. Here's a little 3D printed copy of my head, tiny and made out of copper. Behind me, I have a large one made out of plastic. And at this point, I'm just kind of trying to collect all the different materials. So here is a quick overview of normal FDM 3D printing. FDM just stands for fused deposition modeling, or in essence, it's just melted plastic. So all you do is you melt plastic out of a nozzle right here. The plastic comes from a spool like this. And then you just squirt the melted plastic onto a build plate in layers until you end up with a complete three-dimensional part. And you can get very decent quality at this point. The startup cost is very low, as little as like a couple $100 for honestly a pretty good printer. The main problem is you can't traditionally print in things other than plastic. So if you want something like different density or material properties, temperature resistance, electrical conductivity, you can't get that with just regular plastic. And then metal 3D printing is a much more complex, much more expensive system. It uses powdered metal traditionally, and then some kind of energy system. This might be a laser source. It could be an electron beam. It can be microwaves. And then the energy is absorbed by the powdered metal. The metal fuses and gets stuck together. And then it's built up layer by layer, just like FDM 3D printing. The process is compatible with more materials. So you can do both plastic and metal. With plastic, it's usually called by a different name, but it's the same basic principle. And then other than safety and usability, a main difference precluding its use is price. So it can cost $250,000 to $1 million or more just to get started. And then the material costs are very high as well. So just again, quick overview, FDM printers, cheap, safe, easy to use, but limited in materials. And then powder bed fusion or traditional metal printing, wide choice of materials, but expensive and not easy or safe. And then this brings us to the subject of this talk, which is using special filaments. So just the things that would go in your normal FDM 3D printer. And instead of filling them with pure plastic, filling them with some kind of other material and then printing with them. And then finally, usually you'd want to remove the plastic and combine it so that it's just the pure material of choice. And so it's possible to outsource this process. There are also professional systems that do this. Desktop Metal is a famous company out of the Boston area that is printing metal in this way. But there's still business to business, and their systems are still a couple $100,000. So I'm talking about just plastic special filaments that you can buy just commercially, and then you can print on your existing printer and then post-process it yourself. So that's what this one's about. And so I just want to watch a video I made of one particular part about copper, showing the whole process. It's 2 minutes long. And then this is about chainmail. That's the end result. And we 3D print with just a regular 3D printer. This is a FlashForge Creator Pro. And this is our part with plastic mixed with metal. We then pack it in a protective refractory material inside of a crucible. Cover it with carbon. I'll explain the purposes of each of these steps in a moment. Put it in an oven, just like making a cake. Take it out the next day. And we have a complete metal part. There's our part once more. And here it is under a low power dissection microscope. So we can see just that it has densified. We can see the individual grains. So that's just a quick overview of the whole process. And now I'm going to go into each step one by one. And so step 0, of course, is you need this special material. So it's just filament, just like regular 3D printing filament. It prints very similar. It can be a little bit more brittle, but it's just meant to go in your existing 3D printer. There are a couple of small modifications you might want to make, but it's not necessary. You can put this in any printer and then 3D print with it. And so this is an example of copper filament, which has a density of 4.5 grams per cubic centimeter, as opposed to PLA, the material that it's based on. So just the pure plastic, which is a little bit closer to 1 gram per cubic centimeter. And then there are a few different providers. I'd be happy to share these. There's the Virtual Foundry, Markforged, and BASF. These are the main providers of metal filament in the United States. Markforged and BASF are kind of industrial professional grade, where they have services that will do the post-processing for you. and give you very consistent results. Whereas the Virtual Foundry has a larger selection, sells to consumers, and their process is meant to be compatible with just kind of hobby level equipment. So this is the one that I'm using, is the Virtual Foundry. And then this is just the filament close up. We can see that it has little copper powder embedded into the structure of the filament. In the next step, we actually print with this. So here are a few examples of parts. In general, the filament prints quite well. It can be very abrasive though. It's filled with metal or glass or ceramic. And so it helps to have a 3D printer nozzle that is is resistant to this abrasion. So I'm using a steel nozzle that costs a few dollars. And then this is kind of a problem I'm still dealing with, and you get better with experience, is it can be brittle because it only has a little bit of plastic, just enough to keep it together. So try to avoid sharp turns in the extrusion path. It can also help to keep the room a little bit warm to make the plastic a little bit more malleable than usual. This is a nut and a bolt. This is a cutaway actually of a rocket nozzle engine. People have actually used this to make working rocket nozzles. And then these are just dog bones for tensile testing. Here's a view of a couple of parts that have been printed. These are dog bones. So these are the green parts, or the parts that still have plastic in them. And we can see the the layer lines for a vertically printed part with the copper embedded in it. And then we can compare it to a horizontally printed part. So a lot of the same considerations for regular 3D printing apply to this. You got to be careful with your overhangs and bridges and things that if you're used to regular 3D printing, you're aware of. This is an optional step. I added this one in at the last minute. If you don't have some of the equipment, you can send your parts after printing into a service. So this is the main way that like BASF filaments operate, is they expect you to send it in to a service, and then they'll professionally sinter it and then send the parts back to you. Whereas even though the Virtual Foundry, which is what I'm using, even though you can do it yourself, they also realize that some people prefer to send the parts in and get them professionally sintered. So if you don't have the equipment, you can stop here, ignore the rest of the talk, and get better results than the results that I've gotten kind of DIY style. If you are brave, you can go on to the next step, and that is the debinding of the part. So the part was originally printed with plastic mixed with metal, and then we have to remove that plastic somehow. And there's several ways you can do this. You can dissolve the plastic away. Some people do that. You can catalytically decompose the plastic. So one commercial method uses hot nitric acid, which I personally try to avoid using. And then probably the easiest method, the one that I'm using, involves thermal decomposition. And so this is very convenient because it uses the same equipment as the next step. As you'll see, it uses the same oven. And all you do is you take your green part and you pack it in basically sand. It's aluminum oxide. This has been used a few times. It still works. And you put it in the oven. And then you're left with what they call in industry a brown part. So a part that has had its plastic removed and is pure metal, but is very porous and weak and brittle. And then the last main step to the process is you sinter the part together. So you take your part in your crucible, and how I do it is I put carbon on top and then cover them. And then what this does is the carbon scavenges oxygen, and it also releases, to some extent, carbon monoxide, which will react with any existing oxygen in the part to create carbon dioxide. and so it can act as a reducing agent. And in industry, what they'll use is they'll use nitrogen, argon, or hydrogen. But this is kind of instantly upgrades your setup to be significantly more expensive, and your consumable cost goes way up and the safety cost goes up. Whereas this oven, you can get an oven that can do this without outside gas supply for about $600 on Amazon. So you can buy these ovens for just normal ceramic use. And so, whoops. So here's the part in the oven. And then after taking in the oven, these are our solid copper parts that have been sintered. And then, this is another optional step. You can post-process your parts. So once you've sintered them, they're metal or the other material. And you can do what you would do to those parts normally to post-process them. So here I'm using HCl. There's actually problems with this. Contact me before you clean your parts with HCl. You'll get something called bronze disease when using copper. But you can also sand your parts, machine them, weld them, tap them, solder, or do anything else you would normally do to your part. So for instance, machining, very often after you do this process, people want to machine the part and make the shape, more precise. Here is just a chart showing off, this is showing off the steps in the process. So if you are doing everything in your own oven, so you're doing thermal debinding to remove the plastic as well as sintering, this is what the profile will look like. You'll start at room temperature. You'll gradually heat up to the point where the temperature you thermally debind at. You'll hold there for a while, and then you'll ramp up to the temperature you sinter at, which in the case of copper might be around 1050 to 1080 Celsius. For steel, it might be closer to 1200. And then for other materials, it's going to be different. And then the whole process takes about a day. And we can see up here, this is what the individual particles might look like at the very beginning. And then as we sinter over longer periods of time, or depending on the temperature, they densify and form these grain boundaries. And they never reach full density, but the longer you hold them and at higher temperature, the denser they'll be. So once again, here's a green part that comes out of the printer. Here's the part that comes out of the oven, or if you were doing chemical debinding, just after you remove the plastic. And then these are parts that come out of the oven. And so we can see there's very little change in the shape of the part from the green part to the debound part. But then after debinding, we see some rounding of edges, maybe a little bit of blobbing, and then definitely shrinkage. And if you don't shrink, then you're not actually sintering. So shrinking is very important for successful sintering to fill the voids where the plastic was, and then also between the spheres of the material that you're interested in itself. So here are some results, some actual quantitative results with copper and some, pretty pictures. So on the bottom, and then from the left, we have these green parts, and then sintered at progressively higher temperatures. And we can basically see that if we want to preserve our shape, we kind of have a limit over here. This is at 1060 Celsius. And then as we sinter more at higher and higher temperatures, we get something that's basically just like a copper sphere almost. Doesn't hold its shape very usefully, but is fully dense and quite strong. And so the densities that I've managed to get with this method, the best density I've gotten where the part holds its shape very well, like for instance, this one, and this is also dependent on part geometry. I can get 75 to 80% density. Whereas if I heat it up more to, not much more, but let's say 1074 Celsius as opposed to 1060, I can get up to 95% density, but my part shape really suffers. And so this isn't actually a hard limit. In industry, they can get more, you can get more dense parts without this warping. One of the reasons I think is actually the presence of oxygen in my setup that inhibits sintering, and it can be overcome by an increase in temperature, but then this also results in some warpage. So there are my heads and some I-beams and some cubes. So temperature drives densification, not very controversial. I've done tensile testing of these parts. So just for copper, I think I'm going to speed through this, assuming I have a way to make it go faster. So I'm just using a standard tensile testing rig. I flatten these out and I'm pulling them apart, and I'm checking for ductility, Young's modulus, and then peak tensile strength. This one hasn't been normalized yet, so this is just in force, but just take a look. This was 1060 Celsius, and we got an extension of about 3 millimeters and a load of 650. And we can see it's not very, whoops. Excuse me for one sec. And on the inside, it's not very beautiful. So there's significant porosity and some carbon inclusions at this temperature. And then this is printed at a higher temperature.
700 newtons, 800, 900, 1,003 millimeter extension, 1,100. This is where it broke before. 1,150, 1,200, 4 millimeters, 1,300.
And we get some very good extension and a very nice necking that occurs. Before it finally breaks. This is a little different, but before at the lower temperature, we had a force of 600 newtons peak force. And then at the higher temperature, we had a peak force of closer to 1,500, so more than twice as much. And then our ductility was also about twice as high. So we were getting 50 to 60% extension, which is pretty close to the ideal for just wrought copper. Here it is a little bit quantitatively. Here's a couple of examples in form of stress strain, where at the lower temperature, we're getting a peak stress of about 120 megapascals, and between 0.2 and 0.25 peak extension. Whereas at the higher temperature, we're getting close to 250 megapascals and 0.6, which again is very close to wrought copper, and actually a little better than what you'd get with selective laser melting. Copper is not very well formed with traditional metal 3D printing for a couple of reasons. We also looked at the printing orientation. So normally the strength with 3D printing is quite anisotropic. So if you print something vertically like this, and you pull it this way, it'll delaminate or break much more easily than if you printed it horizontally like this. And so this is true for green parts, but for sintered parts, we didn't really see this nearly as much. So there's quite a bit of noise. Whoops. There's quite a bit of noise in our data, but it's a pretty unconvincing trend, if there is one, that there's a difference between the printing orientations once you sinter. So that's at least something we don't have to worry about as much. I've had very strong parts that were vertically printed, and I have had weaker parts that were horizontally printed. So, just not really one of the main variables to consider if you're worried about strength. Here are some optical images of some etched structures. So at 1060 Celsius, we have these nice crystals and I guess some twinning. And I'm not really honestly sure of the proper metallurgical terms. I'm not a metallurgical, I'm not a scientist in this area, but it's, much more irregular shapes here. We've got these large crystals and very small ones as well. I took these images with a custom rig actually I made during my undergraduate, my master's degree. So for scanning two-dimensional surfaces over a very large area at pretty high resolution. Some similar SEM images. So on the left, we have 1074, and on the right, we have 1060 degrees sintered at. And one thing you can notice, you probably noticed, are these pits. And so this is, my guess is this is a carbon that's trapped from the thermal debinding process that's escaping during sintering. It creates these pits, and they are able to leave at higher temperatures. So this is one of the disadvantages of using this thermal debinding process as opposed to chemical or catalytic. Sometimes I'm a little kind of brutally honest with our shortcomings with the technique or in the lab. So this process is definitely far from optimized. Both of these dog bones were sintered in the same conditions on paper and printed from the same file, everything the same, but we get these two dramatically different structures. And I'm very interested as to why, because I'd like for my process to be more consistent. But for whatever reason, the one on the right is maybe twice as strong and ductile, like printing it at a higher temperature. So I think the temperature drives the formation of this structure. But for whatever reason, it's an inconsistent process, maybe heating and cooling time or something like that. I'm not entirely sure yet. Warping is something to consider. So very fine details can be removed in the process. So for instance, here's a coin. This is a Roman coin that I scanned with my 3D scanner. This is the depth map of the coin. I then 3D printed it. So this is the green part. And then I sintered it. So this is what came out of the oven. This is what it looks like after washing. And then this is what it looks like after it's aged and patinaed for a little bit. This is a scan of the same part with my scanner and a closer look at some of the crystals on the surface. And then here's a comparison between my original scan of the original coin and then the final sintered part after I scanned it again. And so we can see that the features have blurred quite a bit. Part of this is from the printing process, part of it's from the debinding process, and then part of it is from the sintering process. So all in all, there's going to be some blurring of fine details. I am kind of interested in whether it's possible to take a scan of your final part and then apply some kind of inverse compensation on the original part to reverse this warpage, but it's something to consider. Another big question people have is about shrinkage. Is it isotropic? And the answer is no. Even fundamentally, in ideal conditions by an industry provider, shrinkage is not isotropic. because negative space does not shrink. And what I mean by that is when you sinter something, the metal shrinks to fill the gaps. But if there's no metal in a particular location of the part, it won't shrink. So if you have a donut with a hole in it, that will shrink less than if you have a solid disc, because there's more material to shrink. So if you have a part and you have holes, the holes will get larger relative to the rest of the part. And this occurs in metal injection molding, which is a very similar process, and industrial metal 3D printing. You can do adjustment at the CAD level, basically, in your original part to compensate for this. Or probably what's most practical is to print it, see what you get, and then either adjust the model until you get what you want, or you can drill out, like, let's say, holes or machine it to exactly the dimensions that you want. And so this was originally a turtle, and then all of these joints articulated. But after sintering and probably a little too high of a temperature, the joints got so loose that all of the poor turtle's arms and legs fell out of its carapace. So very sad. Here's just another example of this this issue. So this is a nut and a bolt that was printed with this method. What I mean? It's called it's a double-sided bolt. So it has threads that work in both directions, and it's cool. It works, but we could see that the nut is very loose. And that's interesting because when the part came out of the printer, the nut was very tight. So the reason for this, again, is because of this big hole. So the hole did not shrink, but the bolt did shrink. So it became loose. So you should print holes a bit smaller than you would otherwise, or you can drill them out afterwards. Here's an example of a part that would hold together even if it shrank a lot or if it shrank a little, because all of the links are completely interconnected. There's no gap for them to escape through. So whether or not this was green or shrunk a little bit or shrunk a lot, it would still be chainmail. So if you want to print like a mesh, it's a kind of an ideal application for this method. And if you can think of another one, I would really like to hear it, because I'm always interested in other applications. And so we're getting near the end here. This was all about copper so far, but your question probably is, and I know at least one of yours is, what about other materials? So commercially available materials include copper, bronze, titanium, tungsten, aluminum, several kinds of steels. That's a very common one. Magnesium, several types of ceramics, and then very recently glass. But not all of these are easily sintered either commercially or in-house. And I'm not going to get too deep into this diagram, but this basically shows the reactivity of different materials. And what we want to compare is the reactivity of a metal, like let's say copper, to this trend line of copper creating carbon monoxide and dioxide, or carbon monoxide creating carbon dioxide. And the basic rule here is if your material that you're interested in is very low, it's going to be harder to sinter. But if it's very high up here, then it's relatively easy to sinter. So copper is relatively easy to sinter, and then magnesium and titanium are rather difficult and require very stringent control of the gases inside the sintering chamber. But all of these materials you can print relatively easily if your goal isn't to get a pure version of them. If you're okay with having plastic mixed in, then all of these are relatively easy to print in. And then finally, I wanted to talk about one more material, very different than copper, and that is glass. Sintering glass, printing in glass is very special to me because I helped make it for the first time. I visited this company that compounds materials for 3D printing. And this is the compounding process of mixing in fine glass powder, glass beads with plastic. So one more time, this is, it's actually a little bit dirty, but this is just pure plastic, pure PLA. Here it's mixed with glass. And then here it's too much glass where it's it's a good material, but it's not 3D printable. You can't extrude it into a fine enough wire to 3D print easily. And as far as I know, we're the first people to actually do this for regular 3D printers. So it prints just like before, just like the copper filament or regular plastic. This is, again, filled with glass, and it prints to me surprisingly well. I would use this as just a regular plastic. We can see like just like little glass beads on the perimeters of these walls. And then debinding and sintering is just like that with metal, but it's a lot easier because you don't have to worry about oxidation. Glass is already an oxide, ceramics are too. And I was quite surprised to see that actually they sinter really well. They debind and sinter, and you get this nice pure looking substance that holds its shape very well. It probably shrinks more isotropically than with metals so far for me, which lends it to the idea that part of the reason for that is because of the presence of oxygen. So nice shrink. It's clearly not transparent. Most of the reason for that is because of the presence of air or porosity in the part. But part of the reason is also that the refractory material, the stuff I pack it in the crucible, it's an oxide and it sticks to the glass at high temperatures. So here is under a microscope, we can see these sharp shards sticking to the surface. And so one thing I wanted to try was using, instead of aluminum oxide, I wanted to try packing the material in magnesium sulfate, which is a salt. And then the idea is that I could sinter like usual, but then if they were stuck to the surface, I could wash them away afterwards. And this worked. Doesn't work at a very high temperature, but for certain applications, this is a good method. And then we can see that as the temperatures increase, especially like above 1300 Celsius, I've tried between 700 and 1300 Celsius, the glass starts to become transparent. And I think it's possible to get all the way there, maybe if we use smaller glass particles next time. And then porosity is often cited as a problem with this method. Because the parts are not fully dense, not fully strong as the native compound that you're interested in. But sometimes porosity is interesting. So here's a video I made, which ended up being one of my most popular videos, where I printed these little plugs and then I'm sintering them in the oven, same as usual. And then I'm using the plug as a filter. So I just printed this conical shape and I stuffed it into I forgot the name for this thing, a funnel. Thank you. So I just stuffed it into a funnel. And then, well, now I actually am applying suction and I'm using it to make coffee. So this is probably the least practical way to make coffee anyone has ever, tried to do. But I have my coffee, I mixed it with water, I provide suction. And then over the course of a very long amount of time, I can get a very small amount of coffee filtered through this. which I then drink, flagrantly disregarding this no food or drink in the laboratory sign. And it actually tastes pretty good. No major particles in it, very clean. And so if you want to make very weirdly shaped filters for a very specific application, this is a really good way to do it. And then you can control the at least average particle size, the average pore size with temperature. So, you know, that there's another method of control you have there. And then this is my last slide, I promise, just so you can listen to the sound of the glass. And you can see that at a high enough temperature, the glass densifies enough that it does hold water. This is water boiling inside a very thin glass vessel. This was actually 0.6 millimeters thick when I printed it. And so with that, I am completely done. I have some links here for if you want to, let's say, buy this material or check me out on social media, like and subscribe, and send me an email. And other than that, I am done and I'm happy to take some questions. Thank you. And if not, I'll just sit here and stare at you.
Hey,
I have a question. You have done mainly in copper, but have you tried different materials? Yeah, or this is what you're predominantly worked on?
I have some different materials. I have 17-4 steel. I have bronze. I have copper. I have aluminum oxide. I have zirconium silicate, and I have a very small amount of tungsten. The ones that I've tried sintering, I've tried steel, copper, bronze, and glass.
So what are the differences? I know some of them you pointed out in the slides, but the ones you haven't, you know, what would you say would be some of the key factors in getting a more densified product, you know, looking into the variations in the materials?
A densified product, for ceramics and glass, I think it's primarily temperature. I think you can probably just kind of keep upping the temperature and you'll get a denser and denser part. For metal, the problem is if you increase the temperature too much, it'll melt. So in industry, they can get very, very close and very precisely right up to the melting temperature, but not quite. But you know, with my setup, it's just a little bit more janky. It's got some cracks in it. So I think if you're willing to invest in better equipment, you can probably get pretty dense parts. And then the main thing that's kept me from doing some of the filaments, some of the parts, is actually just like not all of it is really easy to use. So like some ceramic filament is very brittle, and I've just been focusing on some other areas. Eventually, I'd like to get back to them, but it's just not so much fun to use, at least with my setup right now.
Gotcha. Thank you.
Yep, you're welcome.
Aaron, one question. You mentioned some materials. What is your sense of mixing hydroxyapatite with some plastics? Do you think that it's doable?
Would it break down at high temperatures?
I think it will, but do you think that we need to do that melting phase?
So the only method of densifying that I've tried is the sintering. So at some point, the material has to survive high enough temperatures to sinter. So it's possible. I mean, if you just had a powder and you wanted to compress it in a mold, maybe you could get a dense thing with just pressure. But that's a very different method.
Mm-hmm.
Yeah. I would like to try that though.
Okay. Thank you.
Sure. If you want to have a collaboration on that, like making filament, I will be getting some equipment to make filament soon. So if you're interested in a collaboration, I'd be happy to talk more with you about that.
Okay, perfect. Thanks.
Hey, Aaron, can you hear me?
Yep, I can.
Yep. So my question would be like when you select your melting, the sintering temperatures for your copper, do you just try and go as close as to the melting point, or is there some kind of guide for you to kind of choose what temperature that you're picking it at?
So there is a guide. So the company that I'm using here has sintering profiles available. And then I just modified mostly the peak temperature based on the experiences in my oven. So because the temperatures are kind of very sensitive, most people are going to want to try the stock instructions and then just tinker with it a little bit until you get the properties you desire. And then the main trade-off behind like whether or not to go right up to the melting point is warpage versus density and strength. So the higher the temperature, just universally, you'll get a denser part, but it will warp more. And so it all depends on how stringent your part has to be. So if your part absolutely needs to be a certain shape, you can get a very precise shape like that bolt that I made, but you just have to print it a little bit cooler. But then, of course, you're trading off the density and strength for that.
Gotcha. Thank you.
Yep.
One other question from my side. What is the best resolution you can get?
Do you mean like minimum feature size or? Yes. It's very close to the resolution of the printer itself. So the parts that are printed that are sintered at a relatively low temperature, where they only shrink a few percent, the features are pretty much entirely there. So like this one with the bolt, it looks pretty much exactly the same as when I put it in the oven. The only difference is that it's, pure metal. But this is probably only about maybe 60% as dense as the pure copper.
So your resolution is going to be in something close to 0.5 millimeter?
Yeah, I'd say about there. It does, the overall shrink though might vary a little bit from print to print, but the actual minimum feature size is probably about there, yeah.
Okay.
Something I haven't done a whole lot is post-processing. Even in the industry, like the industry standards, very often they will post-process these. So they'll drill out holes exactly how they should be, and they'll mill the sides and things like that. I haven't done a whole lot of that yet though.
All right, thanks.
You're welcome. So far, we've gotten 60% of our participants asking questions, so there's only 2 people left. So it's their turn. Is there anything anybody wish that I talked more about that you were maybe more interested in? If I ever give this talk again? Awesome. It was perfect. All right, I'm going to just add in the chat, I'm going to add all of these links. If anybody's interested, I could also just post the, whoops. If anyone's interested, I can also just post these slides. But if no one says I want the slides, then I'm not going to give them. All right. Ryan, what do you think?
I
Should we
think
take
it's
it
good
over?
to have these slides if possible.
I'm sorry?
I think it's good to have these slides if it's possible.
Okay. All right. I will share these then. I can do that.
Thank you for this great webinar and for all those attended. We'll also have this posted up on our website in our archive for anyone who wants to go back and relearn the lessons we've learned today.
Okay.
And yeah, I hope you all have a really great day. Thank you so much for attending.
Okay. I did just post the link to these slides on the chat. So
I'll give it a second.
all right. Make sure I don't have any bad comments in here.
All right, perfect.
Okay.
Thank you everyone for attending, and I hope you have a really great day.
All right. Thanks, everybody.